Alright, I'm going to solve some problems on equations of motion, normal and tangential coordinates, and recommendation for you to study the sample problems. And he has one that resembles F1310. So let's look at this one. It says a sports car is traveling along a 30-degree banked road with a radius of curvature of 500 feet. If the coefficient of static friction between the tires and the road is 0.2, determine the maximum safe speed so no slipping occurs. Neglect the size of the car. Okay, so the car will tend to, if driving too fast, will tend to slip away from the that is towards increasing the radius of curvature. So we need to set up free body diagram, and so draw a free body diagram and state the equations of motion. Okay, so this is the axis of curve that includes or the center of curvature is along that axis, and this is the bank, and we have the car, and I'm drawing it as a block. Okay, and so we have the angle theta, and you saw I sketched the forces acting, so definitely we have the weight of the car mg. As you can see, there's no indication of what the mass of the car is, so expectation is for the mass to cancel out in calculations. So, and then I have the normal force reaction from the surface, and then we have the friction force, and this is the limit case. So the friction force, it opposes slipping, the car slipping outside towards increasing the radius of curvature. 500 feet. So this friction force, and it's static coefficient of friction times normal force. Okay. All right, and then we have, remember, if you add acceleration on a free body diagram, you use dashed line, and this is the normal acceleration. All right, so with some forces in the normal direction, positive is towards the center of curvature, and this is mass times normal acceleration. Okay, and then we also need to write equilibrium along the vertical line, because there's no motion there, so it's sum of force equals 0. No motion, no acceleration in the vertical direction. Okay, so we have angle theta here, as well as same angle theta is, okay, friction force, and erase it, make room for the angle. All right, friction force mu times n. And this is theta as well. Okay, so for the in the radial direction, let me see, am I doing the right thing? Yeah, in the radial direction, we have n times sine of theta. Okay, this component sine theta. And then plus mu n would be cosine theta, this piece here. Okay, I'm not showing the components, I'm just staying with the I have a capricious lamp to my left. Okay, so and then the weight does not have a component in the normal direction, the direction of un. So this is equal to mass, and normal acceleration is velocity squared over radius of curvature. Okay, so what do we have? What are the unknowns in this equation? I have n unknown and v unknown. So I need a second equation. I said we're going to sum forces in the that will be the binormal direction, and these are zero, the vertical force. Binormal is the vertical direction. Okay, so what do we have? We have, and it's positive up, so it will be n cosine theta, and then I have negative nu n sine theta, negative mg equals 0. So these are the two equations. We have two unknowns, v and n, and we can eliminate n between the two equations and keep v as the unknown. Okay, so from the second equation I have n equals mg divided by cosine theta negative nu sine theta. Okay, and then I'm going to plug this into the first equation. So mg sine theta over cosine theta minus nu sine theta, okay, plus mg, or it's rather mu mg cosine theta nu mg cosine theta nu mg cosine theta over cosine theta minus mu sine theta equals m velocity squared over rho. Okay, so m simplifies out, and I have velocity equals, it will be a square root of this whole thing divided by rho. So I have g sine theta plus nu cosine theta over cosine theta minus nu sine theta, okay, equals so 32.2 feet per second squared sine of 30 degrees plus nu is 0.2 cosine of 30 degrees over cosine of 30 degrees minus 0.2 sine of 30 degrees. Okay, so V equals, let me pause while I'm doing the calculation. Have I paused? All right, so the answer is 7.941 feet per second. That's the velocity. Let's move to a new problem. Is this one 1352? A girl sits motionless relative to the surface of a horizontal platform at distance 5 meters from the platform center. Angular motion of the platform is slowly increasing, and we need to find the maximum speed. Will be the speed of at which the girl will just before she sleeps off the platform. Coefficient of static friction with the girl in the platform is 0.2. Okay, so problem 1352. And you see I sketched the solution here. So we're assuming this to be like a side view, and it's rotating. Theta dot would be, and here like a block. The girl model, the girl is a block. So it's on bearings. And what do we have given? We have the radius. They used R. Okay, R 5 meters. And then there's the normal force. So imagine I should have made the platform in dashed line. Okay, so we have the normal force. We have the friction force. It's nu times n. And then of course we have weight, mg. Okay, and normal acceleration, an, or centripetal acceleration. So sum of forces in the normal direction equals mass times normal acceleration, which is mass times velocity square over radius. To the left, in terms of forces, we have so vertical equilibrium, no motion, so it will be essentially mg equals n, or n equals mg. So friction force, it's nu mg equals now, so this was sum of forces, just one force, equals mass times velocity squared over r. Okay. We're not given anything else, so really mass of the girl is not relevant, and we have velocity as square root of mu gr. Okay, mu 0.2, 9.81, and r is 5. Okay, so 0.2 times 9.81 times 5 equals, so this is 2.236 meter per second is the answer. All right, not a problem with a figure from the author. Problem 13. 54. Okay, 1354. And here what do we have? We have a cable that runs through a hole. There is no friction between the cable and here where it's changing direction. And there's a mass A that's 15 kilograms. There is a mass B that is 2 kilograms. Radius is 1.5. Friction is negligible. Everywhere in the fork, the cable is inextensible, and it's massless. And it says, what is the speed of the block? So we have an equilibrium state, dynamic equilibrium state, where the tension in the cable which is induced by the weight of mass A, it's causing the centripetal acceleration. Now, if we, so yeah, this is the problem. Let's solve it to where there's a coefficient of friction. Okay, so if there is a coefficient of friction, there will be a range of speeds for which the radius is maintained constant, for which there's no change in radius. Okay, so one would be where the weight A is at the verge of dropping, and the other one is where it's at the verge of, due to centrifugal force, we can use that, it's used in practice, is about to lift A. Okay, so we have R 1.5. Again, it will be, I'm putting a star here because I'm assuming a coefficient of friction. Let's make it 0.2 like in previous problems. Okay, so there's the tension in the cable, there's the normal force, there's the weight, mg, and then at low speeds it tends to slide towards the axis of rotation, the mass. Okay, so slides towards the and it means that friction force is oriented this way, friction force, and this is N times nu, essentially mg, nu mg, and this will be a static friction, so static friction, because there's no relative motion between the platform, the table. Okay, so yeah, I can say tension, and this is, what do we have, M, I used M, but this is an MB, MA times G. So clearly tension in the cable is MAG. Yeah, I'm going to write equations of motion when the speed is at the verge of moving the mass A up and having the block B sliding out. The friction force reverses motion, reverses. So I'm showing it in here. This will be the other case, friction force for case 2. This is for case 1. All right, so case 1, we have acceleration again is normal acceleration, AN, positive towards the axis of rotation. So I have sum of force, I'm writing sum of forces equals mass of B times normal acceleration. Okay. All right, so for in general, so case 1, there will be tension in the cable, which we know it's MAG. And then I have negative mu MB G equals mass of B, velocity squared over R. Okay. And again, tension is, so I'm replacing tension with MAG. Okay. So velocity is going to be, there is a G that moves in front, so G MA minus mu MB over MB, and then times R, and then it goes square root. Okay. And then for case 2, okay, case 2, I'll have, so this changes to a plus, and this changes to a plus. So it'll be a small velocity, minimum in pencil, maximum in with the plus. Okay. Okay, so we can we can calculate these two minimum maximum speeds. V min equals V max equals, and let me pause while I'm doing this. Okay, so I did the calculations. The minimum velocity 10.36 meters per second, maximum when we'll start to slip outside is 10.64. And if in any of these equations you make mu equals 0, you get the answer for the problem the way it's formulated in the book. 10.505. Okay, so this was another problem that we did, and I'm going to do others.